I hope you can see my slide.
Yeah, it's visible, sir.
Yeah. So first of all, thank you very much, and Dr. Deepak and all other admin team. They invited me in this talk, and they have given me a chance. So in this talk, what I'm planning, first I will start with a basic introduction of this medical imaging techniques like X-ray, CT scan, and MRI. Means how a radiologist form all these images. Um, and to be honest, I'm not a radiologist. I'm not a medical doctor, so I can't give you that much information in depth. But as a data scientist, as a computer scientist, I will try to give you as more as possible, the like whatever information we require for computer. So we will start first. We will start with the introduction of all these three imaging techniques. Then after that, we'll do some programming things related to CT scan image and how we can apply deep learning model on CT scan and how we can classify those particular CT scan image. So in that programming part, we will use DICOM. We will use DICOM image. Then we'll convert the DICOM to NumPy format. And once like we convert to NumPy, then we will perform deep learning operations. So we'll work on different deep learning models, and I would like to show you how we can improve uh, on different models. Means if one model is not performing good, then how we can improve the performance and other things. So you can see like how differently we can apply deep learning techniques, right? So let us start with the X-ray one. So first of all, X-ray, everyone know about X-rays. So X-ray are form of electromagnetic radiation, similar to visible lights. So let me tell you the overview of X-ray, how we can capture X-ray image. So I think you all might have experience of this X-ray things, like maybe X-ray related to teeth, X-ray related to chest, and or other body parts. So it's basically we use for fracture or accident for if there is a problem in our teeth and other things. So what that particular medical doctor or radiologist do during X-ray time, they ask us to stand in between of that machine. For example, we are going for chest X-ray, then they tell us to take out your clothes and just stand in front of machine. So there's a machine. So there are two parts of machine. One is the source, another is a sink, or we can say like destination. So from source, that X-ray will be emerged, and these X-rays will pass through our body. And on the back side, there is sink. That sink or that destination will capture, will observe those X-rays, right? So actually, like whenever these rays are passed through bodies, then the image of those rays are formed on that sink part, right? So reflection, we can say reflection, we can say image. So these images, like we see X-ray on a particular film or particular like on a particular like plastic film, right? So these X-rays are those generated images through that particular machine, right? So these X-rays are formed from like X-rays, just like a visible light. Right? Visible light also are also a kinds of rays, but X-ray we can't see. Visual light we can see. So medical X-rays are used to generate images of tissues and structure inside the body, right? That I told you. If X-rays travel through the body, also pass through X-ray detector on the other side of patient, and images will be formed that represent the shadow formed by the object inside the body. So that I already told you. Now, if you're going for X-ray, how it work, then I will start with one demo. Then once like I will go through a demo, then you will understand this slide automatically. So then no need to go for this slide at that time. So here is a demo thing. If you can't hear, then please let me know, right? So yes, we can see demo things. Okay, so this was the quick demo of X-ray, means how that X-ray is formed. As I told you earlier, there is a source and sink. From source, this X-rays will pass, and this from source, this X-rays will emerge, and they will pass through that body, and on sink, like image will be formed and shadow will be formed. So here there is a one important point. Those image will be formed. So if you see X-ray clearly, then for bony part, we can see the clear structure. And for soft tissues like our muscles and some other part, we see some like shadow kinds of things, right? Because in bone we have more calcium, right? Calcium, high density. So X-ray observe bony part more due to those calcium, due to those high density things. So that's the reason we get clear image of like bone part, but that's shaded kinds of thing, gray area for that like muscle part, right? So these are things, and whatever you have seen in the video, it is written here. So when X-ray, you all know this answer. Where can we use X-ray? Like for bone fracture, for certain tumors, for other abnormal masses, and pneumonia, some other type of injury, like foreign object. Foreign object means something go from outside in a body that we can detect with the help of X-ray. Dental problem, all those things open. We can use this X-ray things. Now after X-ray, we have computed a tomography, CT scan, that is also very popular nowadays, because CT scan is far better than X-rays, because if you are going to capture X-ray, that means the two-dimensional formation of image. X-ray, CT scan, X-ray is a two-dimensional image, but if you're talking about CT scan, then it's a three-dimensional one. So same X-ray we use in CT scan also, but in the form of three-dimensional format. So if you're going for CT scan, then we can get more detailed information. So here you can see this machine. I think few of you might have seen this machine either in movie or in television or in real life, right? So here we have patient table, then a gantry and gantry aperture. So here a patient will lay here, then a patient will go inside this machine, and this gantry will capture these X-ray images. So here a gantry will move. Inside this gantry, there is a one particular device. From that device, X-ray will emerge, and then using that X-rays, several images will be captured. We can say several slices will be captured, and in the end, all these slices, two-dimensional slices, will be combined using some mathematical function, and then a 3D CT scan will be formed. So this is a way we captured a CT scan image for a particular person. So here, first of all, if you want to see demo, then we can go for demo, then we can discuss about other things. Okay, so this is about CT scan. And like whatever you have seen in video, it is written here, like how we capture CT scan image. So in place of two-dimensional slice, we get three-dimensional image from CT scan, but we use only X-ray only for CT scan image also, right? So we can say it's an extended version of that X-ray, like X-ray in two dimensions, CT scan in three dimensions. So we can get detailed information using that CT scan image, right? So why we use CT scan? There are so many reasons. You all know, like for brain tumor purpose, like for heart, if there is some abnormality in the heart, right? For lung cancer purpose, or for different other lung-related disease purpose, we use this CT scan image, right? Then next is MRI, magnetic resonance imaging. So it is different than both X-rays and CT scan. MRI is a non-invasive imaging technology. Non-invasive means here we don't pass any rays, right? In X-ray and CT scan, we are passing X-ray, right? That can be harmful for body. But MRI is a non-invasive, means we are not passing any rays, but we are generating magnetic field, right? We are generating magnetic field inside the body, and in body we have proton, right? That those are like made with water. So these protons are stimulated with the help of that magnetic field. Means if we are going through this, like if we are uh, going for this MRI scan, this proton will go in the opposite direction of magnetic field. And once we will stop that processing, means MRI processing, then this proton will realign with that medical field, this magnetic field. At that time, the energy will be released by our tissues, right? Tissues by our organs. So how much energy is going to be released, that will decide, like using that energy only, we will create MRI image, right? So we'll see this thing here also, like we have one demo, and the same thing we'll see here for MRI. You can see this side. Then, so this was about this MRI image, and here like we can go for MRI, like we can do knee MRI and brain MRI, and like so many like body parts can be used. Like MRI can be used for like for different body parts, and this is the most effective techniques, like better than X-rays and CT scan, and specifically like MRI we use for soft tissue purpose, right? A CT scan and X-ray, like in most of the cases we use for like for bony part, right? Fracture kinds of things, for teeth kinds of things. But if you want to clearly see the soft tissues, then we use magnetic resonance imaging, MRI image things, right? So this is the like difference, and let me go to the other part. So now we will do some like we can say hands-on, or we can do some programming things. So what I'm going to do, I have some CT scan images for chest. collab. Right. So I have like CT scan. Let me show you CT scan images. I uploaded all these images in Google Drive. So here, DICOM. Here, this. These are trained models. You can ignore these two files. If you see rename, then here we can find this one is the DICOM image. In that, like we have ID of patient, like the file name is saved with the ID of patient 0094, age of a patient 92, and contrast 0, and CT scan image. Right. So this image is in DICOM format. It's likewise we have other images also. Right. We will see here. So there are total 100 images in this folder. And one important point is, if you rename, then this point, like here, if it is mentioned 0, that means it's class negative. If it is mentioned 1, then it's a class positive, right? For chest ray, like for particular disease, like maybe pneumonia or something else, like we are doing. So let me find if I can see something with class 1. So most of them are 0. So like few are with 0, few are with 1. So likewise, like we can see whether it's a class 0 image or class 1 image, we can differentiate with that, right? So we'll see in the programming part that thing. So first of all, here we would like to view that image, a particular DICOM image. How can we visualize those particular images, DICOM images? So for viewing purpose, if you are not interested in programming things, you want easier solution, then there are different softwares, Radiant, DICOM, 3D Slicer, Micro, DICOM, Horus, like that. So you can use these softwares for like viewing that DICOM image, either CT scan or whatever, MRI or whatever. Like you can view all everything with the help of this DICOM. Then if you are interested in programming part, then we are here for that. So first of all, as I uploaded all my data set, complete data set in DICOM in my Colab folder, right? And in my Colab folder, this is a particular folder, DICOM directory. And here we have all images. So we are working in Google Colab and our data set is Google Drive. So we need to connect Google Colab to Google Drive. So for that purpose, we can use this from google.colab input drive.mount. This is a basic operation, so I think you all are aware. And we need to provide our Gmail account permission, right? If you want to work with Google Colab in Google Drive. So connect with Google Drive like that. So this is the way we can work. And then we can see. Once it will be connected, then we'll change your path. So now it's mounted, and then we need to reach inside that DICOM directory, right? This is DICOM directory. So this path I provided, my drive Colab DICOM directory. This path I provided. Now you can see all files, like using ls, we'll see all files are there. So actually I already trained this model earlier. So these are the trained weights. So you can ignore these first two files, right? If you want, you can remove this one. But like we have these images, DCM file, the DICOM image. So clearly you can see like here class 1, here class 0, like that. Okay. So these are the total 100 images, 100 CT scan images. Now, we need to work with this DICOM is how we can see DICOM information and all other things we need to see. So like if you want to visualize everything, if you want to visualize these DICOM images, then we need to have this PyDICOM. So we need to install this PyDICOM. So just we install this pip install PyDICOM. Then after this, just we are going to import some necessary libraries. Here, first, like let's perform operation on only one image at a time, right? We are going to perform operation only on one image at a time. So if you want to perform operation on only one image, then what we can do, just take single image, single DICOM path, contain directory, my drive, colab, like that. So this just any one image name we have taken randomly, like any one image we have taken from this list, right? From this list. Then once we set up the path, then pydicom.dcm read we do. So DCM just like CSV read, I think you know about the file to read CSV file, right? In the same way, we have DCM read to read DCM file and single file. So once we do this, then number of rows, number of columns. So we can see 512, 512. That's the size of particular file resolution, image resolution, right? 512 rows, 512 columns in that particular CT scan image. Right, then we can see a patient name. For example, here is some like clear name is not written, some code word is written because we don't want to display that patient information. So just code word related to that patient. And body part examined, so it's chest, so it's chest X-ray, so like that we can find it. And if you want to see complete data in DICOM, means you want to display all the metadata related to DICOM file. So just simple for loop for element in DICOM file, print element. Once you will do this, so here you can find everything like group length, specific character set, image type, right? And so many other things. Unfortunately, I cannot explain all these things because these all are related to medical doctors, but I can give you an idea about few of them, few of these things, like modality, right? Modality CT. This is a manufacturer, is scanner company, like a company like Siemens, and what else? So patient name, patient ID, right? Patient birth date. Right? So few informations are not given here because radiologists don't want to provide specific patient related information, right? Due to privacy, right? Ethics policies and privacies. So patient like male and what else? So like so many things we can see here. Like somewhere you can find the image resolution also 512 and things. So like this, number of rows, number of columns, 512, 512. Pixel spacing means we are talking for CT scan, then like pixel spacing means how much like one pixel is far away from another pixel, like in terms of distance. So this is spacing and what else? Okay, so that's it. Like this thing, this many things we can see here. And here, this is the particular value, 524288. That means image resolution 512 of 512. So if you will see the complete total number of pixels, this will be a 524 and 288, including some extra information. So then if you want to like display, we want to take out that particular image, two-dimensional image here. So DICOM file.pixel array we will do. So if you see the DICOM file is safe, then 512 we extracted from that complete DICOM file. And if you want to show that image, then just simple matplotlib plt.im so we can do. So np DICOM file compare cmap gray. So in the form of grayscale image, we can visualize, we can see that particular image. So we have seen like 512 is the like row, 512 the column, and we can clearly see this particular CT scan image using DICOM. Now, once we extracted this part, right? After extracting this part, we don't require the DICOM file, because we need only this thing, right? Till this point, just we need only this DICOM things. Then what we can do, like further operations, we can apply, we can perform only with the help of this variable np DICOM file, right? So just we are going to import CV2, and now what we are going to do, we extracted information, but we want to perform operation with the help of NumPy, right? Using NumPy, not with the help of the DCM, right? Because the NumPy is very cost effective. Cost effective means like it takes less memory, right? So in this like part of code, we will convert that DICOM file to NumPy1. How to convert the DICOM to NumPy? We'll do that thing. So if not operational path exists, what we are going to do, let me show you in this directory, my Google Drive. So here, one folder we have DICOM directory, DICOM_dir, but another folder I will create, NumPy directory, or I already have here, but I will create again using that code. So whatever DICOM directory, in whatever files are there in this DICOM directories, all these files will be copied to NumPy directory, but in the form of NumPy format, right? If you see the rename in the form of NumPy format. I already ran this code earlier. That's why, like you can see this file. If you want, I can delete it. But if I will delete, it will take a bit more time if I will run it again, right? So here I will explain you how I converted this DICOM directory, DICOM file to NumPy file, numerical Python file that we'll see here. So if a folder is not exist, then just we'll create this folder, right? Target folder. Now for file name in operating system list directory source folder, right? We are taking this source folder. Source folder is this one, right? Source folder is this one. Target folder is this one. So if you are taking source folder, we are taking file name in operation list directory source folder, means we are taking all files from source folder. Now what we are doing, if file name dot lower dot ends with DCM. So what we are doing here, like sometimes what happen, dot DCM is in a small case, sometimes that is in a capital or mixed format. So what we are going to do, first of all, we are converting into a smaller one. Everything should be smaller one. Then we are going to match files those have .dcm extension, right? .dcm extension. So here, like for example, this file where we have, you rename then .dcm extension, right? We are looking for .dcm extension. So if file name .lower ends with .dcm, file path, operation path .join, source folder, and file name. So here we are going to fetch a particular file, right? One by one, we want to fetch like all files from that particular folder. So source folder we have taken, and then we are passing this file name, specific file name, right? Specific file name from this source folder. For example, in this case, the specific file name will be this one, right? This complete file, right? This specific file name. So once we are getting this one, then we are going to create a complete path with source folder. In source folder, this one, right? And / file name. So once we are getting this one, DICOM data, pydicom.dcm, just we need to read that file. That's the same thing we did earlier. And file path, we need to read that particular DICOM file. And if pixel data in DICOM data, then if pixel value is there, then just we need to copy that pixel array, right? DICOM data dot pixel array means we are copying that 512 cross 512 part, right? We are copying that only that part. We don't require other metadata like patient name, patient information, right? Or like scanner name and all those things. We don't need. We need only this pixel array, right? So this pixel array is inside this DICOM data. So we are going to fetch it. Once we are getting this, then just we are going to resize this. We are changing the shape like from 512 to 256 using this interpolation. Then what we are going to do, we are making a target folder, right? Inside the target folder, we are going to mention one file, right? Inside the target folder, yeah, like we are going to write that file with .numpy format. So here what we took, what we did, we have taken just array 512 plus 512 array. Now we are going to save that particular array. Like later on we convert it into 256 also. Now we are going to save this particular 256 array in .numpy format, right? So just we are writing extension .npy. Here we are adding operation on the path, split text, file name, right? And zero part, right? Zero part means accept that .npy format, accept that npy format, or accept that DCM format. We are taking that file. For example, let me show you here. So what we are doing with the help of zero, we are taking this part. Till this point we are taking, right? Because we split it with the .dcm, and this part we are taking, and in place of .dcm, we are applying .npy. So that's it. And just we need to save this file. So np.save output file path. So output file path we have already provided earlier, right? So you can see where this one, I output file path and dot comma resized image. So whatever resized image we have taken, that just we need to save, like we can save this in a particular, that particular folder, numpy folder, right? So this processing is for one image. We did for one image, but we have for loop for all images, right? All DICOM images. So they using this for loop, we can convert all our this their DCM image to NumPy format, right? This is a simple thing. Now, once we did this, let me run everything. So it will be okay. It will save time, right? So now, once we did this, we are then we can see this NumPy folder path, content drive, this NumPy folder path, like our Google Drive path we have right here. Now we need to work using work with the help of this NumPy folder only. So once we have this one, then just we need to read all these files from this NumPy folder, operation.list directory NumPy folder, like that. File name ends with .numpy, and just we are going to load all these files, np.load, because these are NumPy formats. So np.load we can do, and operation path.join, NumPy folder, and file name, right? So here we are going to write the NumPy folder, right? This one, and particular file name, and that's it. And image.append image array. So here what we are doing, actually, like we don't want to read from image all the time. We are creating one array, image array. So in image array, we are going to collect all images, right? We are going to store all images in image array. So for that purpose, just first of all, like we are going to load that particular image, and we are just going to write, or we are going to append in that image array, right? So if you do this, there's a problem. It is taking time in the NumPy one. Okay, so here, then once we do this, then we can see the shape nparray.image x, whatever shape it is, then we will convert that shape to 100, 256, 256, 1. So here 100, there are 100 images. Each image shape is 256, 256, and this is a channel. Like we have only one channel in this particular CT scan image. So once a shape will be printed here, after once this processing part will be finished, then you will see shape here 100, 256, 261. Then now what we need to do, we need to find a label of that image. As I mentioned in the beginning, like label means class label we can find with the help of file name. So here we are exploring that particular file. We are exploring that particular file with that name. So for file in operation list directory, right, NumPy folder, label.append file.split underscore. We are doing underscore. So let's understand this thing with the help of image. So if we rename this file, if if you rename this file, then different fields are separated with the help of underscore, ID underscore 096, age, is like that, underscores. So now we can see, as I mentioned earlier, like this 0 represents class 0, 1 represents class 1. So we need to extract this class 0, class 1. So this is the second last value, right? First last and second last value in that file name. So we need to extract second last value. Those are separated with the help of underscore. So if you see here, what we are going to do for file in operational list directory numpy folder, label.append file split underscore -2, right? So -2 means second last value we are going to fetch with the help of this numpy, and just we are going to take that value in y is a label. So just we are going to print, so 100 labels will be there because 100 images, 100 labels. Then here we are doing to just train test split is a simple process like train test split using sklearn we are doing, and we are dividing the image into training part and testing part. 80% training, 20% testing we are taking. So we have divided into this part. Then if you see, now we got four out of these two parts, like train image and test image, we got xtrain, xtest, bytrain, bytest, 4 parts. So if you see the pixel intensity value of this xtrain.max will be, you will see that the maximum value is 4095. Now you might be confused here because maximum intensity value should be 255, right? So if you're talking for CT scan image, then we don't use in a particular intensity value. We use Hoff field, right? We use Hounsfield, right? Hounsfield units. So what are these Hounsfield units? Like these represents the depth of particular like CT scan image, like how much will be the depth. It depends on a scanner, what kinds of CT scanner we are going to use. So it might be like 12-bit scanner or 16-bit format scanner. So if you're talking for 12-bit image scanner, then in 12-bit image scanner we have like like if it's a 12-bit, then intensity range will go till 4096, right? And if you're talking about 16-bit image scanner, then intensity range will go from 0 to 65535, right? So in the same way, we can represent this thing. And we can also have a Hounsfield unit value from -1000 to 1000. So if it is negative, then it will represent the air in the body. Plus 1000 is a soft tissue. So likewise, like radiologists or medical doctors can identify whether it's a soft tissue or like other just air part, right? So that's the reason we have maximum intensity value 4095 here, right? In the same way, if you see minimum, we can see minimum here, right? And just we need to normalize the image. I think you all know the normalization procedure. So I am not going in the deep of this normalization. Simple normalization we are going to use means we are dividing that xtrain image with maximum value. So this our image will be normalized here. And just if you see the shape, then it will be 80 to 56 to 56 one. Why 80? Because out of 100, 20% went for testing part. So only 80 images for training part, and image size is 256 to 56. And here just we are converting that particular label into two categorical. Two categorical means like one hot encoding we are going to use, right? So I think you all all these things you have already covered. So I'm not going in the deep of all these, like with the one hot encoding and other things. So like just use your previous knowledge, like whatever knowledge you gained in previous lectures. So I think you are aware about this one hot encoding. So we are converting in one hot encoding. Now we are creating our convolution model, right? Simple convolution norm model we are going to create with the help of few convolution layer, pooling layer, and all those things. So from Keras layers model regularization, and here I think you already know about this models.sequential. And here, like we are creating one convolution layer, convol 2D, two-dimensional convolution layer with 64 number of filters. 3,3 is the kernel size. Padding is same, means whatever the image input size, we want same output size. We are using kernel regularization, means L2 regularization we are going to use. This is also called big regularization. And we are taking input shape 256, 256 because we already know our image size is 256, 256. So we are taking this one, and then we are applying once we did this one, so I think you are aware, if you are applying convolution layer 60 with 64 filters, so 64 different types of features we can extract from this convolution layer, right? 64 different types of features. So I think in previous lecture, someone asked question, how model know like in what part like we should focus, right? On what particular part of image we should focus, how model will know. So model will know with the help of these features, right? 64 different types of features we extracted from convolution layer, right? Then using those features only, like model will identify what these features are. How they will identify? Because in the beginning we provide labels, right? We provide labels along with the input data, right? We provide input as well as output, right? You can see here by train, by test, we provide by train also. Once we'll do training later on, we'll provide X train as well as by train also. So here we are providing input and output. So with the help of that output things, label things, our model will learn the things. The model will identify the features, like what kinds of feature it is, right? So in this way, we can work on. So 64 different types of features will be extracted. Then here we are applying activation ReLU. So what is the role of ReLU activation function? To activate a particular neuron, right? Which neuron should be activated? Because here we apply ReLU, which is a non-linear activation function. Most of the things in real world are non-linear. Here, in simple way, you can understand. Linear means, for example, you are going to university from your home. If you are going in a single direction, it is like 99.9% it is not possible like you will reach to your university. You need to change your direction, different paths you need to change, right? Until unless your home is not very near to your university, right? So that's why like we need like non-linear things. That's the reason we use this non-linear activation function. So what this activation function will do, it will tell to that like whatever features we generated from convolution layer, and this activation function will tell what particular features should be activated more, means like how much weights we should assign to a particular extracted feature, whether we should assign high weight or we should assign low weight, right? So if features are important, then we will assign higher weight. If features are not important, then lower weight, like that. So this so like using activation functions to activate a particular neuron. Then again, we are applying convolution layer because in the beginning, just we extract low level features. Low level features are just pixel value and a small part of image. Those are not good for for identifying purpose, for recognizing purpose, for classification purpose. So what we should do, we should go in the deep, like we should get the detailed features, high level features we want. So for extraction high level features, we need more than 2 convolution layers, right? More than 1 convolution layer. Only 1 convolution layer will not be sufficient. So we have another convolution layer with 64 features and same regularization. Regularization here is used to reduce the overfitting problem, right? So we are not going to discuss overfitting in detail here, but you can understand, like here we want to remove overfitting issue, we want to reduce overfitting issue. That's why we applied regularization with very small value of that learning rate, right? And then again, we apply max. So here max pooling is like, for example, like we have image size 512 cross 512. Here in this case, we have 256, 256. If we are applying convolution layer on 256, so many multiplication and addition we need to apply, right? All these multiplication and addition increase the computational complexity, right? So, so if they increase the computation complexity, then we need high processing power, means we need powerful GPU. So we don't want to like waste our resources. What we can do, we can use pooling layer, either max pool or other different types of pooling. And pooling layer will reduce the size of image. Like for example, 256, 256. If you are applying 2-dimensional pooling with pool size 2,2, then 256 will be converted into 128, 128, right? So like that, we can do this pooling one. Then again, here we are applying another convolution layer, same. Why we are applying? This region is same. We want high level features. So same activation, convolution, and like that we repeated this like few times, right? And we created one model, this CNN model. And in the end, we are using this flatten, right? We applied all these max pooling and other things. and we are using this flatten. So flatten, the purpose of flatten is to convert two-dimensional image to one-dimensional one. So here, like for example, if you are applying convert 2D, then our output will be two-dimensional one, but we need to convert that to one dimension if you want to do classification, right? Because for classification purpose, we need to apply dense layer, and dense layer needs input in one dimension format. So layer to dense to activation softmax. So here, like I have written activation softmax, number of output 2, but if you are writing 1 here, an activation sigma, that will also be possible, right? In the case of binary classification, our output shape, our number of output can be 1, but in that case, we need to apply activation sigmoid. But if it is a multi-class classification problem, then it is mandatory that we need to apply, we have to apply softmax activation function at the last layer. And here, like whatever number of classes we have, that number of classes we will mention. Like for example, 10 classes, then we need to mention 10. It is a mandatory condition. We can't change this one, right? So once we run this model, we'll see this model summary, then we can find all these model, right? I'm not going in the deep of this. So then here you will see like we need to set our compilation parameters. So Keras optimizer SGD we are doing, learning rate we set this one. We are applying categorical cross entropy and optimizer SGD and matrix accuracy like that. Then once we did this, and then we are also applying augmentation, right? Because we have only 80 images, right? These images are not that much. So we want to generate few more images with the help of data augmentation. So again, for augmentation purpose, we are using this image data generator inside that Keras pre-processing library. And here, like we rotation range, like 40 degree, like we are going to rotate image width shift, width, height shift, shear range, like all these different operations we are applying, we are generating different images. Then we are applying, we are doing this model.fit, means we are doing training. So for training purpose, we need to pass training data set, right? Training input, training this X-train, Y-train, right? Batch size we are taking 10, epoch 10, and validation data set also we are going to take. So here we are taking batch size 10. What do you mean by batch size 10? Because total number of images are 80, right? In a training data set. So batch size 10 we are taking. That means we don't want to pass all these 80 images. The reason is if we pass all these images, that is called like a stochastic gradient descent. If we pass all these images, then that's called batch gradient descent, sorry, batch gradient descent. If we pass all these images, then what will happen? We will update weight only once, right? These all are like built deep of that deep learning techniques. It will take a bit time if I'll explain. So for example, if you're passing all 80 images, then in one epoch, our weight will be updated only once, right? And all images, all 80 images will be passed to update that weight for a single time. And due to that, like we require high computational cost, right? And so what we can do, we can use batch processing. We can divide our images into batches of size, let's say 10 here. So if you're dividing all 80 images into batch of size 10, then in each batch there will be 8 images, right? So that's the reason for 8 times this model weights will be updated, right? Or different like images will be passed in all these things, and accuracy, loss, validation accuracy, validation loss will pass through. And here for all these 10 epochs, we are getting accuracy. In the beginning, like our accuracy will be low, then slowly it will improve. Sometimes it can decrease also, right? Then losses, validation accuracy, validation loss, validation loss or this training loss will reduce, but accuracy will increase epoch by epoch, right? So in this way we can do, and we can evaluate this model on test data set. So here we can see this loss and accuracy and loss we can see of the training for test data set. So X test normalize, and we are going to do test one. And here we'll plot this curve. Then if you see this curve, right, it's a simple matplotlib function, accuracy, validation, accuracy, and all those things. So it's a simple matplotlib. So I'm not like explaining these things in detail. But if you see this graph, then this graph is not proper. Means we are not getting very good answer. There's some problem. This is an overfitting case, right? Still we applied regularization and other things, but still our model is overfitting. right? Because our test data set is going this side, training is going this side. So this clearly there's an overfitting issue, right? Here loss, this test accuracy is not improving at all. So this is a problem. So we need to remove this problem, reduce this problem. So for that purpose, I will explain one more model quickly, right? And here in this model, what we are going to do, same, we are using kernel initializer equal to HE uniform. Means earlier, like, we use this convolution layer. In the convolution layer, we have filters, right? These filters values are assigned randomly in the beginning, right? So if you are taking two random values, right, just random values, then sometimes it creates problem, right? So what we can do, we can initialize this kernel with the help of some method. So here we are using this HE uniform kernel initializer. So it will assign a value in some little bit intelligent way, right? And so just everything is same. Like we are using this kernel initializer and batch. We are also using batch normalization here. The purpose of batch normalization is just like a normalization. Means whatever features we are going to get from convolution layer, all those features will be normalized, right? And what batch normalization do? It makes our process fast. Means conversion, right? Our model converge fast if we are going to use batch normalization, right? Then activation, convolution, activation like that. And we are also using dropout here because our model was overfitting. So we try to use dropout, and but because earlier like our regularization was not working, right? So we tried a different method, dropout, for dealing with this overfitting problem. So we removed regularization from here. We used this dropout. And the same way, like we repeated the same thing because we want high level features. Then we repeated the same thing for different models like that. Then flatten. And here, here also we did some change, layered advance to 56, right? Dropout. Then again, like we added one more dance layer. Earlier we used only one dance layer. We added one more dance layer here, right? Here also we assigned these weights, and dropout we used, right? So we'll see this model, and if we print this graph, and one more important thing we change, like we are using optimizers SGD, right? Stochastic gradient descent optimizer we are going to use with learning rate momentum. And one more important thing we are doing, early stopping criteria we are going to apply. So early stopping means like we are monitoring validation loss, but we'll see for 10, patience equal to 10, means for 10 epochs we'll see. Actually, here we are going to run only 10 epochs, so it will not work. But if you, in reality, we need to run our model for 100 epochs or 200 epochs, right? But it will take time. That's why I run for 10 epochs. So in this case, if you are using patience equal to 10, that means for 10 epochs, you will see this loss, validation loss. If it is not increasing, if it is not like validation loss is not decreasing, right? For continuous 10 epochs, either it is like increasing or the same, then we should stop our training at that time. So we use this early stopping criteria. Then we use the model checkpoint, means we need to save our best model, right? It's a best model weight, right? And why? How we'll check it's the best? We'll check the mod equal to max, means validation accuracy. So we maximum, that will be considered as the best model. And then we are going to reduce learning rate, reduce then we are using this adaptive learning rate here. So for that purpose, we are using reduce LR on plateau. So this is one of the method, mathematical technique. By that way, we can reduce this learning rate after a certain number of epochs, because the reason is in the beginning, we require high learning rate, but once like we'll go towards conversion, right? We require that learning rate should be reduced because our gradient reduces. Well, like for example, for first 20 epochs, we require very high learning rate, means weights will change drastically. That you can see in any of the model, like if you're going to train any model, if you'll see this thing, right? In the beginning, like the weights will be changed drastically. Like for example, accuracy, 4.6, 4.7, 5.3, like from 4.7, it jumped to 5.3, 53%, 53 to 58, because the beginning. In the beginning, change will be high, but once we'll go at the end side, means we have like near to 100 epochs, then these accuracy and all these losses will change in a minor way. Minor way means that weights, updated weights will be very low. Getting in mind? So that's the reason we should have high learning rate in the beginning and low learning rate in the beginning, in the end. So for that purpose, we are using this adaptive learning rate with the help of reduce LR on plateau. So accordingly, like the change learning rate, again, same augmentation we are applying, and we are applying this model dot fit. We are doing this fitting this model, same thing, but along with the other things, previous one, like we are going to using this earlier stopping, MCP shape, reduce LR, these things we are passing. And once we learn this, once we learn, then evaluate another thing same. And once we plot this, it's far better than previous one, right? Here our loss is improving, right? So it's quite better. Not we can say it's not an excellent solution, but it's quite better than the previous one, right? So this is the way like we can work on. There likewise I have other different models for improvement purpose, but due to a time constraint, I think I should stop here. And like you can see like different models, like here clearly like it is better than the second one, right? It is improving the second one. So in this case we applied, let me check. So we applied different layers. Like earlier we were, I was applying so many layers. So our model was a little bit overfitting. So I reduced number of layers, like only 2 or 3 convolution layer, right? Then flatten and all those things apply. Right, so this is the way like we can work on, and we can see, right? So different models on the basis of different criteria we can use. So in this way, like you need to work on your programming task. Once like you are going to train any deep learning, machine learning model, then you need to check different hyperparameters and other things. Many students, like when I give talk, or many students ask me how to improve my model, and it's not performing well. So there is no fixed formula for improving any of the model. There are some tricks. Tricks means like we should know about the things like what learning rate do, what batch processing do, and so many like what optimization, what the purpose of particular optimization function, and loss function. So we should choose all these, how many layers we should choose, select, how many filters we need to select. So many different things are there. On the basis of that, you can like know how your model will perform better, right? So all these things come with experience. So once you will get experience, then automatically you can train your model. But one trick I would like to say here, if you want to work, if you want to train your model, if you want to finalize your model quick, then try to adapt model from already pre-trained models like ResNet, LXNet, BGNet, and so many other models are there, right? MobileNet. So try to see their structure because they are well qualified models, right? They proved themselves. So try to adapt the same structure. Little bit here and there you can change, but try to follow the same format, right? So in that way, like you can improve your model, or you can finalize your model quickly. So I think that's it from my side. Thank you very much. Let me know for any question.
Yeah, thank you, Professor Sandeep, for your informative talk and for showing demonstrations on CNN by analyzing each and every step carefully. So now, if participants, if are having any query, you can write it and write in the chat box. So Sandeep, they can only write their query in the chat box. They cannot unmute. I can interact with you directly.
No problem. I can see in chat. I open my chat box. If any question, please let me know, participants.
Oh, good.
Okay, so how many number of epochs we should take to train the model? As I told you, like there is no fixed method and formula. It depends on your data set and depends on your model, how many layers you are going to take, and how complex your data set is. Like in your data set, so many small parts are there, and you are classifying those parts. Like for example, there's a big ground, there's big playground, and that playground, small flowers are there, like flowers are there. So you need to classify, you need to detect those flowers. Then you should have large number of epochs, right? In the same way, if you have like a big ground, and in that just a small image, there's one image in that there's a large size of object, so you don't require that many epochs. So it completely depends on data set, complexity of data set. If there are so like noisy data set, then we require bit more epochs, because convolution layer will feel will face problem in extracts, like feature extraction, if no data set is noisy. So we require large number of epochs. So many different factors are there. On that basis, we select number of epochs. So number of epochs, sometimes only 100 epochs are more than sufficient. Sometimes 1000 are also not sufficient, right? It depends. Is there any specific advantage of DICOM over other similar formulas such as NetT, etc.? No, here we cannot say advantage or disadvantage. Actually, these medical doctors store their images in DICOM format. Whenever you will ask data set from medical doctors, then most probably they will give you data set in the form of DICOM format. So DICOM format is not for us, just like computer scientists. This format is for medical doctors, right? So we need to convert that data set, that format, to our format, either NetT one, right? That's very good, and or NumPy one, right? For our fast processing purpose. I think it's clear. In DICOM we can say like several like metadata, and we don't require those metadata. These metadata information is just only for doctors, not for us, right? So that's the reason we convert this DICOM to this thing. Any other question, please?
Yeah, I think so. There are no other questions. If they have any query, they can drop an email to you.
Definitely.
Yeah. So thank you so much for joining us, sharing your expertise with us.
Thank you.
Thank you, sir. Thank you so much.
Thank you, sir. And I'm going to leave it now. Okay. Fine.
Yes, sir.
Thank you.
Okay.
Thank you. Bye. Bye.
Bye. Sir. Good night. Okay, participants.